here, including and after we've exhausted the questions from the general audience, then Robyn and her committee will go into a session where we'll continue to ask the questions and then make a decision that about passing Robyn and the thesis defense. So I think that's it. And Robyn, why don't you go ahead and get started?
Sweet. Okay, so I'm excited to be here and telling you all about my research I've been working on for the past 2 years. I'd like to thank you all for coming, and especially thank you to my advisors and committee for guiding me through this and all of their help over the last couple of years. And so my thesis is titled Water Woes Worsen, Middle Rio Grande Reservoir Modeling Projects Declining Water Availability Under Climate Change Scenarios. And so the background, this is the Middle Rio Grande, a bit downstream of the reservoirs that I'm looking at. And so some quick facts on the Rio Grande. It's one of the longest rivers in North America, at 1,759 miles long, which I think ranks 4th if you include the whole of North America. And the watershed is 182,000 square miles. And the river as a whole provides drinking water for over 6 million people and irrigates around 2 million acres. The surrounding watershed is predominantly semi-arid, which just means that there's not much other water around and means that the river's all the more important to the region. And it is one of the most fully utilized rivers in the United States, meaning almost all the water flowing through it is used. And so the Middle Rio Grande starts in southern Colorado in the Rockies, and then flows through all of New Mexico, and then forms the border between Texas and Mexico. And the area that I looked at for my research, we're gonna go to the next slide. There we go, is in the southern half of New Mexico. And you can just barely see it here, but if we zoom in, there's 2 sub-watersheds that I looked at. And most of the water flowing through my study area actually originates in the mountains up here. As you can see, it's pretty dry down near my study area. So around 50 to 75% of the water flowing through the study area originates as snowpack. And so the snow melt runoff is in the spring, but most of the water use for agriculture is during the summer. And so one of the reasons that dams were built are to control the water for agricultural purposes. And so the Elephant Butte Dam was completed in 1916 as part of the Rio Grande project. And it has a capacity of around 2 million acre feet. And it was built primarily for irrigation and flood control. Another thing that played into it was a treaty between the United States and Mexico, guaranteeing deliveries of water on the Rio Grande. And the Elephant Butte Dam Reservoir is also used for recreation and power generation. The other dam in my study area that defines the second subwatershed is called the Caballo Dam, and it was completed a bit later in 1938. It has a smaller capacity of around 325,000 acre feet. It was built primarily for flood control and is used to fine-tune delivery amounts to downstream users. And it also has a secondary use of recreation. the upstream boundary of my study area is the San Marcial gauge, which is a USGS gauge located a little bit upstream of Elephant Butte, and that is used as the stream flow into the study area. And so the water being released from Elephant Butte and Caballo flows downstream to downstream users. It's almost, I'd argue, more of a like a delivery channel than a river at this point. But there are around 160,000 acres of irrigated agriculture that the Elephant Butte Caballo Reservoir system provides water for. The primary crops are alfalfa, pecans, and vegetables. And you can't see the area of agriculture from the zoomed out view, but if you zoom in on any sort of satellite imagery, you can see either side of the river, there is agriculture going on, at least within the area that you can get water from the river to the fields. And then the other main user of water, though lesser extent than agriculture, is urban use. And so the cities of El Paso and Juarez have a combined population of around 2 million people, and around half the drinking water in El Paso comes from the Rio Grande. And other than the Rio Grande, water that's being used is coming from groundwater, but that is more expensive due to the cost of pumping it, drilling wells, and it's also finite. The Elephant Butte and Caballo reservoirs are heavily managed, and the amount of water released from them depends on the amount of storage and the amount of stream flow. And the release policy is detailed in the 2008 operating agreement, which has been the most recent update to reservoir policy. Water is distributed to users according to water rights. People own water. And a term that I want to talk about, because I'm going to use it later, is full allocation. And when I'm saying that, I'm referring to the full amount of water that people are allocated in their water rights, which is what they'll receive as it's available. But if it's not available, you can't give people water that isn't there. And so that'll be coming back later. And so with changing climate, the first thing you think of is increasing temperature, which is probably the most distinct part of it, but it's really everything about the climate is changing somewhat, and it's influencing hydrology. So as I said before, 50 to 75% of flow is coming from snowmelt runoff, but the snowpack has decreased. No, sorry, we're getting more people. The snowpack has decreased around 25% from 1958 to 2015. And April 1st is significant because that is historically peak snowpack, and it's used to make projections on what the stream flow will be for the coming year. And farmers can base how much crops they're planting off expected water availability. But if the whole hydrologic system is changing a bit, there's now more uncertainty there. Modeling of snowmelt runoff that goes into the future, there is a project that looked at that for the Upper Rio Grande and made projections for the year 2100. And their research showed that peak flows will be occurring around 14 to 24 days earlier in the year. And that snowmelt runoff volume might change between an increase of 7% to a decrease of 8%. And that variability is coming from different climate simulations. So that's all happening on the upstream side of the watershed, but more locally to the study area, I'm looking at evaporation from the reservoir surface is a big part of the water balance. Historic losses from Elephant Butte have been around 8 to 20% of annual releases. And so around up to 1/6 of the water coming in is being lost to evaporation. And the evaporation rate has been projected to increase by around 8% by the 2080s based on some modeling done by the Bureau of Reclamation. That part of my research is based off. And if the evaporation rate is increasing, the local water balance is also changing. And so this is Elephant Butte Reservoir from above. The left is when it's relatively full. This picture happened to be taken in 1994. And then on the right, it is quite empty. And this was taken in 2013 during one of the most recent severe droughts. It isn't the dates don't imply that it's a linear less and less and less water. It's a highly variable system. And so throughout the whole life of the dam, there have been times when the dam is full, times when the dam is quite empty. And the concern isn't that it's happening at all. The concern with climate change is that it might happen more often, that there's low storage and low releases from the reservoir. And
Say,
so
Robyn?
Yes.
Sorry, could I interrupt just for a moment?
Yeah.
If we go back to that picture, could you point out where Elephant Butte Dam is?
Certainly. It is at the bottom.
Okay.
And so the really dark blue part is right behind the dam. And
why is it dark blue?
because it's deep. And
yeah,
so
very good.
Going up. Oh.
Yeah. Maybe you were going to answer my next question, which is, do you know where San Marcial is on this picture?
It's definitely at the top end, but I don't know exactly where. I think it's like in these bends, but I'm not sure.
Yeah, fair enough. I'm sorry we never had a chance to take you there. It's actually on the left picture. You can see a little mesa where the river makes a bend. And that
Here?
right there. Yep. And San
Okay,
Marcial is just at the base of that mesa to the west, to the left.
Okay. I guess one other thing I can say is there's a lot more surface area for evaporation when it's full than when it's empty, and that'll come back later in my results.
While we're interrupting Robyn about these pictures because they're so fascinating, the picture on the right is about the way it looked earlier this year. So there's another severe drought.
Yeah, it is. I looked this week and I think it was 6.5% capacity of the reservoir right now. Things aren't looking great at the moment. Also, Alex, your sound is really muddy today.
Sorry,
I don't know if that's something you can fix or not. I think it's been like that before. And then you've like moved a microphone or something. I don't know. Okay, so this is a quote that I thought really just summarized the situation very well and stuck out to me for how concise it is. 19th century water law, 20th century infrastructure, and 21st century population growth and climate change are on a collision course throughout the West. And I thought that hit everything, or all the big things that are going on, and how if we just keep going with the same policy and management, it's just not going to work out the same as it has. And so the research that I did used global climate modeling to project water availability into the future. And the global climate models that we used the output of were part of the coupled model intercomparison project, phase 5, which is a modeling project where all the global climate models have some standardized aspects of how they are set up and like when they start. And so that you can look at a whole bunch of climate models that have been developed by different research agencies and actually compare the results and look at them as an ensemble, because each climate model parameterizes different aspects of the global climate using different equations, and there is no one correct way of representing the world in a system of equations. And the phase 5 of CMIP uses the representative concentration pathway to have 4 different scenarios for human response to climate change, essentially. And so depending on how much reductions in greenhouse gas emissions and other human variables, it lays out 4 pathways for some of the forcings on the model that influence how climate change happens. And so there were around 27 or 30 global climate models that we used their outputs for our reservoir modeling. And so here's a list of all the abbreviated model names to acknowledge them. The full names are way too long to put on a slide, but the names aren't incredibly important. But I also in the background have a visual of, I guess, like the grid size of what a global climate model in CMIP 5 looks like. And so one grid cell would be larger than our whole study area. And so the outputs that come out of global climate models have just too large a resolution to be useful for local hydrological modeling. And so there is a statistical procedure called bias correction and spatial disaggregation that was done to the global climate model data set. And it essentially takes a historic period of measured variables and a historic period of the modeled variables and corrects for regional bias and variability, so that within that historic period, the model data has the same average and variability as the actual historic measured values. And so then those factors are applied to the model data going into the future so that trends are still there, but it removes any sort of regional bias that the global model has. Because as a whole, the global models do quite well, but there are some variables where regionally they aren't quite hitting the historic average. And so then it gets adjusted. And this makes it usable for local hydrological modeling. Okay, so my research questions that I was addressing for this project. First, how is climate change expected to affect water availability in the Elephant Butte Caballo Reservoir system? And will climate change have a greater impact on water availability in the headwaters or locally? And then next will be methods, but first, this is the butte of Elephant Butte. And so the modeling that I did Well, I worked with a reservoir water balance model that accounts for inflows and outflows out of the reservoir. And the model was run at a yearly time step between 1971 and 2070. We ran 97 different simulations through the reservoir model, and each climate simulation was a combination of one global climate model under a representative concentration pathway. And the reservoir model solved iteratively at each time step because there are interdependencies between surface area. For example, surface area affects evaporation, which affects volume, which affects surface area. And so using iterative solving allowed us to find the balance at each time step. And then one other detail of the model is that it lumped elephant butte and caballo together essentially by fixing caballo at a constant volume. Caballo is operated more seasonally, but on a year-to-year basis, it has around the same average volume, whereas elephant butte is used for more long-term storage and has a lot more variability year to year in how much is stored in it. So fixing caballo at a constant volume was a reasonable assumption. So the reservoir water balance used in the model is dsdt, change in storage per change in time, is equal to the stream flow in plus the precipitation on the reservoir surface minus evaporation from the reservoir surface plus runoff from the surrounding watershed minus releases. And that will give you the change in storage for a time step. And then I put a dashed line across to represent that there is a surface area factor going on in there as well. And so I'm going to go through those 5 terms in the water balance and where we got the numbers for them. And so stream flow is at the San Marcial gauge. And it came from the BCSD climate projections, which the Bureau of Reclamation was able to model stream flow from them using variable infiltration capacity hydrologic model. And that produced a naturalized stream flow, but that doesn't account for human consumptive use and management. And so Nolan Townsend and Dave Gutzler applied a statistical normalization procedure that adjusted for human use, and that produced a normalized stream flow data set for all of the climate simulations that I was working with. And that was used as input to the reservoir model for stream flow. And then for precipitation, again, it came from the BCSD climate projections. And I used an ArcPython script to spatially average across each subwatershed. So I basically took a cookie cutter and averaged within each subwatershed to find an average precipitation depth. And then that was multiplied by the reservoir surface area to get a volume of precipitation. Evaporation was a bit more complicated because evaporation depends on multiple factors, such as wind speed, solar radiation, but we did not have BCSD climate projections for the climate simulations we were working with. What we did have was modeled evaporation for future climate projections that the Bureau of Reclamation did using the CRLE method. However, that was for the previous generation of CMIC climate projections, and so it did not map directly to the simulations we're using. And so we did a regression. We assumed that temperature is the driving factor. We also looked in precipitation, but that wasn't affecting much. And we did a regression between the deviation from historic average temperature and deviation from historic average evaporation. And so that assumes that if the temperature in a year was 2 degrees above the historic average, the evaporation would be around 50 some millimeters per day above average. And there's a lot of variability in this regression, but it's also a really strong trend, and overall is good enough for what we're doing. So one of the easiest terms was runoff. That was calculated as a simple fraction of precipitation that fell on the subwatershed, and it was routed directly to Caballo. And then finally, the releases were calculated using a simplified equation that estimates the 2008 operating agreement policy. And so it basically said it's based on the previous year's stream storage in Elephant Butte and stream flow at San Marcial. And based on that, if it's below the full allocation, you use the calculated value. But if it's above full allocation, it kind of maxes out at full allocation. And so this is just putting together all of that data flow. And there's the process is done by Bureau of Reclamation, process is done by Nolan Townsend, and process is worked on by myself. And so the last part of methods here is validation. There wasn't a very long period I had to work with because the release operation equation changed in 2008, but we assumed a constant for the whole period. So we only had between 2008 and 2020, but for those years, I found a data set of precipitation, temperature, and stream flow that was measured, ran the model with that, and compared it to the model output to the actual storage and releases. And while not perfect, it does a pretty good job. Some of the discrepancy might come from the fact that farmers can bank water year to year and decide to not use their water this year and save it for next year. But our modeling doesn't account for that because that's a difficult human decision to predict. So we've arrived at results. And before I go into results, a few quick notes. There's a lot of dimensions to the data output by the reservoir model. For each variable, there are 97 simulations and 100 years. And in order to be able to get anything useful out of a plot, you need to average by either the model or the year, or it's just going to be spaghetti chaos. And so in any way you slice it, you'll either be ignoring some of the model-to-model variability or the year-to-year variability. But that's how it has to be. And so first, I'm going to talk about local climate, but we'll go one at a time. So precipitation, For this, we averaged the past 50 years and the future 50 years for each model. And so the lines are the median, and the median simulations average precipitation was very similar in the past compared to the future. But there is more variability between models in the future. So there's less certainty that the precipitation will stay the same. Temperature-wise, all of the models projected an increase in temperature. The median simulation increased by 1.7 degrees C or 3.1 degrees Fahrenheit. And some models increased more than other models, but there's high amount of certainty that the temperature will increase, maybe extremely high. For stream flow, the median simulation decreased by 11.8%, and the variability increased between the model for the simulations. And 11% is a significant decrease in water availability coming into a reservoir. For the next series of plots, we are looking at the releases from the reservoir, and we created 3 benchmarks. 100% of full allocation is a wet year, 50% of full allocation represents a drought, and 25% of full allocation is a severe drought, equivalent to that of 2012, 2013. And so on this plot, the x-axis is the year, and the y-axis is kind of an inverse reliability. And so in each year, we're basically asking every model, did you succeed in releasing full allocation? And so this is the percent of simulations that failed to release full allocation, failed to release 50% allocation, failed to release 25% of full allocation in a given year. And as you can see, the percent of simulations failing to release each threshold increases as we go into the future. This plot shows the same data set as the last plot. We're still looking at releases across the 3 thresholds. However, in this one, we're averaging in the past 50 years and the next 50 years, and each individual dot represents 1 climate simulation. And so this allows us to look at the variability between the climate simulations. And so you can see that in the past, the climate simulations show like around 40 to 60% of years it fails to release full allocation. And then in the future, it's around 5 to 100%. And so there's a lot of uncertainty in exactly how much water will be available. So if you're looking at the medians and the ensemble as a whole, it is most likely that there will be less water available. The next thing that we looked at is consecutive drought, because 1 year of drought is not good, but if there were 5 years in a row, that's a lot more stress on groundwater and economic stress on farmers. And so this plot is similar to the last plot in that each dot is 1 climate simulation. And so look in the past, and the median simulation projects around 10 years consecutively where full allocation is not met. And then in the future, it is around 14 years, but some models are, I guess, probably reasonably projecting around 20 consecutive years, and the most extreme models are projecting up to 30, 40, 50 years in a row without reaching full allocation for release. This is my last plot, and it's a little bit weird, but I think if I walk you through it, you could probably figure it out. What we're trying to look at is the climate change effect upstream and locally. And so on this plot, the x-axis is the change in net subwatershed influence. There was no great way to say that, but what this axis is the precipitation locally minus the evaporation plus runoff. So all the local factors influencing reservoir volume. And each dot is one climate simulation. And the value of it is the change between the past 50 years and the next 50 years. So if it's at 10, that means that the average local influence over the next 50 years will be about 10 kiloacre feet per year higher than it was in the past 50 years. And then the y-axis here is stream flow, which is upstream factors. And a really important thing to note is that the scale is very different. On the x-axis, it's the change locally is plus or minus around 30 kiloacre feet per year, but on the y-axis, it's plus or minus 500 kiloacre feet per year. And so even if here the local influence is positive on the reservoir by 10, if you look over to the y-axis, there's a negative change in stream flow. And so these dashed lines are the median for each variable. And so for the median simulation, there's a decrease in stream flow annually by 58 kiloacre feet per year, and the increase locally is only 4.5 kiloacre feet per year. And then the last thing I want to talk about with this is that there's a correlation where in simulations where the stream flow decreased, the local contributions to the reservoir increased, which was not what I expected. But by doing regressions of a bunch of variables against each other, we found out that this correlation is driven by the fact that when there's low stream flow, there's low reservoir storage, which means low surface area, which limits the amount of evaporation. And less evaporation, since evaporation is a negative term, is a positive influence from local factors on the reservoir. Okay, so moving on to the discussion, some management implications of my research are that it's very likely there's less water available in the future. So water managers and users need to adapt or desiccate, which is some extreme words there. But what I mean is that if you go on doing the same things, there's going to be less water and it's not going to work out very well. So we need to acknowledge that there will probably be less water, and what are we going to do to keep everything running smoothly despite that. Another management implication is that since the snowmelt is a lot more influential than local climate change, this means there's less opportunity for local management changes to close the gap. And if evaporation had been the driving factor of water availability, there might be things that could happen locally to minimize evaporation. That's challenging, but possible. But since it's upstream and climate driven, there's probably not much that can be done about changing snowmelt other than changing how much water we use. And then finally, climate change is increasing uncertainty in the system while simultaneously limiting feasible options. Limiting feasible options means that it's already forcing low reservoir volumes. And so we can't manage the reservoir to be lower. The climate is managing the reservoir to be lower. And so there's just like less choices that we have, while also putting pressure by reducing water availability. And so it's becoming necessary, but also far more challenging to find robust management strategies. And so regionally, less water will impact a lot of things such as agriculture. Agriculture might have to change the types of crops they're farming or the acres. Culturally, low water might influence boating or just enjoying rivers. Economically, tourism and agriculture can have impacts on the economy if water is not managed well to continue to support them. Ecologically, low river flows and more years where the river gets completely dry will impact fish and bugs and birds along the river corridor. And hydrologically, low flows influence groundwater use and groundwater surface water interactions. And so there's a lot of things relying on the river, and that will be affected by the river and by climate change. So addressing a few assumptions that the model I worked with made, it assumed constant management throughout the whole time period, which is unrealistic because the management has already changed from 1970 to present day. And it has potential to change more, which before 2070, which would impact how much releases are made and just the whole system. Additionally, the model I use, as I mentioned, doesn't have year-to-year banking, and rainfall on the farms doesn't have any impact on demand. That kind of relates back to constant management. And then the yearly time step we're using doesn't account for seasonal variability, but we used a yearly time step because there wasn't data available for monthly, and there wasn't a release equation that could adequately project monthly releases. And then finally, the evaporation and temperature relationship was constant during the whole study period. When it changed a little bit during it, and the whole evaporation temperature relationship itself is definitely somewhat of an approximation, though we thought it was an adequate approximation given data availability and modeling concerns. And so in conclusion, a future water availability decreased across all metrics that we looked at. Release volumes, stream flow, and consecutive drought. The snowmelt runoff is projected to be more influential than local climate. And the projections that we made using the ensemble of simulations does have a lot of uncertainty, though as an ensemble, expect less water, but also be prepared for a whole range of scenarios. More future projections will have to be made to help inform policy changes that will be needed in the future. And while quantity of water and future water, like quantity projections, are important, there will also have to be a lot of other aspects that are considered when making policy and management changes and decisions in the future. That's all I have, but now would be question time. I think you can ask questions in the chat or turn on your mic or whatever, but thanks for coming and hearing about this.
Clapping noise or clapping emoji. Thank you very much, Robyn. That was a nice presentation. Any questions or comments from the audience?
I'd chime in with a question. Robyn, what would you say was the most difficult part of this project, and why, and how did you get through it?
I think the most difficult part was understanding the spreadsheet model and how it mapped to the Scilab Python model, because the reservoir model I used had been mostly developed by Alex in previous projects, and then a couple of students had put it into Scilab, which is basically MATLAB. But I had to make sure it actually lined up, but the spreadsheet model was kind of a mess to understand since I hadn't made it myself. I asked a lot of questions, probably 3 times.
Cool. All right, thank you.
More questions or comments? I have a comment / oh, sorry, Noel, please go ahead.
Yeah, well, I'll make it a general question first. Nice presentation, Robyn. Lots of information there. It's hard to follow all of it. Are there things, what would you next do to improve the model? Or another way of asking it is, what is ignored in your modeling that you think would be the next improvement?
I think the 2 biggest things that I'd want to improve would be, they're both pretty big. Having, there's so many things. One thing might be investigating different operation policy, and just seeing how it behaves under different operation equations. Another thing might be looking at monthly time scale, because there's I guess, different amounts of water stored at different times of the year and different evaporation rates at different times of the year. And high storage and high evaporation rates somewhat coincide. So maybe like more in depth look at the evaporation, and then yeah, I guess that would be it.
And just a little question, because I don't know, how much does the salinity in the reservoir change over time? And is that enough to have a significant impact on evaporation rates?
I don't know. I think I tried to find salinity data in your class when I was working on a project, and I couldn't find it.
Robyn, do you think that salinity in general in the reservoir would be increasing or decreasing?
Well, increasing.
And why is that?
Because there's 8 to 20% of, because the evaporation is like a big term. And I guess like if salinity wasn't changing at all, it'd be like the salinity coming in, salinity going, like there wouldn't be of runoff, evaporation, precipitation. Evaporation is a lot bigger than runoff and precipitation. And so there's water leaving without salt at a bigger scale than water coming in. Not a good explanation.
I also just wanted to make a comment that it may be obvious, but to people, but I think like most of our audience is sitting near the lakes, the shores of Lake Superior. And then a couple of us are in, or a few of us are in the Southwest here. And so if you contrast Lake Superior to Elephant Butte Reservoir, would you say, can you say that for Elephant Butte, on average, the evaporation always exceeds the direct precipitation onto the reservoir and the runoff? And then what do you, I know you haven't been studying Lake Superior, but is it the same thing in Lake Superior?
I would guess no. Well,
It's like the flip, that the precipitation directly onto Lake Superior and the runoff coming into Lake Superior far exceeds the evaporation.
yeah, I guess for Elephant Butte, I don't know if I like directly put these numbers next to each other. I don't know if I probably should have said the amount of evaporation yearly. I think I only had it in millimeters per day. So for Elephant Butte, the yearly precipitation is around 10 inches, and the yearly evaporation is around, let's see, 50 inches. I can't
Far
figure out.
greater.
Is it like 655?
I think a bit higher than that, but not
Okay.
much. Yeah, I mean, obviously, big difference.
I was looking at it this morning and I can't remember right now. I can't figure out how to look at the chat, but I saw there's a note in the chat.
I can read them off if you want.
Yeah, if there's questions.
Okay, so from
Manage that.
Patricia Holmes, no relation. What changes upstream of your watersheds might happen due to population changes? Or is that a factor to consider? I know your research focus is somewhat locally focused.
Okay. My guess is that there is room for less water to be consumptively used upstream. But with current policy and water rights, the way they're laid out, there's probably already using what their water rights have, though I guess consumptive and non-consumptive use change. There might need to be like incentive for upstream users to use less than their water rights allocate, or extremely big policy change that I don't know if how much changing water rights is possible. I think that Alex and Dave could have a better understanding of this.
Well, this is an interesting question, and I'll pitch in. By the way, Robyn, you've just demonstrated your ability to get through these defenses by trying to shift answers onto your committee. That's very smoothly done. Good work.
I try to answer first with my opinion that is not very well formed.
So who do you think uses? I mean, where does, Townsend and Gutzler came up with this statistical approach for essentially taking water out of the river. But in reality, where is most of that water going? Who's consuming it?
Yeah, it's probably a lot of agriculture.
That's
upstream
right.
that is consumptive use because of
so if you had to guess, the largest river or city upstream is Albuquerque, which is where I'm sitting, and how much what if you had to guess a number for the water rights in terms of acre feet that the city of Albuquerque can take out of the river in terms of the formal water rights that have been allocated for native Rio Grande water? What do you think that number would be? Just take a guess.
I want to go like 20 kiloacre feet.
Try again. But well, I'm teasing you a little bit.
Per
but
year,
the answer, you could come up with exactly the right quantitative answer. So the rights that the city of Albuquerque has to take Rio Grande water out for municipal drinking water purposes is 0.
Okay.
So it's all going to ag.
Okay.
In terms of now, there are subtleties there because there's actually a bunch of water flowing downstream that's not native to this basin, but that was a problem for Nolan, not for you. So if the question that you were asked is, what might happen due to population changes, and let me rephrase that a bit. I mean, if there's going to be less water being consumed upstream, who's going to consume less? Because they have all the rights now.
There's less water being used.
Yeah, if we said we've got to change policy and consume less water upriver,
if you want to
who's got to give that water up?
Reduction in consumption, it'd have to be agricultural.
That's correct. So that is the policy in a nutshell. The policy decision upriver from Elephant Butte is whether or not to stop growing things. And essentially the corollary to that is that farmers would not have their water taken away. They would make money by cashing in and selling their water rights to cities like Albuquerque that have money to pay them and potentially have a need to expand their use of river water.
So does Albuquerque use river water, but then also use groundwater, so it's like net no consumptive use, and they put back what they took out of the river?
There's a lot of that. That's correct. So there is an extraction and water treatment plant, but in terms of water rights, the only water that Albuquerque and Santa Fe, for that matter, are allowed to take out is water that originated in the Colorado River Basin and was pumped underneath the Continental Divide and dumped into the Rio Grande. But of course, once you do that, the water, we only just make that distinction between native water and non-native water on paper. It's all just water flowing down the river. So
there are a couple more.
Yeah,
Sorry.
Let's get back to having Robyn answer questions.
There are a couple more questions in the chat box. So one from Rob. Were you surprised the model did not show significantly more years when full allocation wasn't met in the future compared to the past? Do you agree that the model didn't show significantly more years when the full allocation wasn't met in the future compared to the past? You want to put that figure back up?
Yeah. I guess. I guess these are both looking at that, and I guess I would say that there is a significant change going into the future, and I don't know if Rob was going for surprised that there wasn't more of a change, or going for statistical significance, or maybe pointing out that there's not like more agreement between the simulations.
What about like the extremes? Are that, on average, I think there are significant differences, but what about like the extremes? Are there significant differences? And by extremes, I mean bad extremes.
I think you made me more confused.
Let me help, Robyn. I think Alex is looking at the orange dots, right?
Okay. Oh,
and the question is, are things getting better or worse between the past and the future? Let's just keep it simple like that.
Okay, things are getting worse in the future.
And if we just, go ahead.
I guess this is if we're looking at orange, like that's a very low benchmark, though I'd say maybe what surprised me more is the lack of years at that in the past, because I know that there have been at least like the 2012, 2013 that was that low in the past, but only like one or two models even had 1 year that bad in the past. So I think it is a significant increase in simulations that are saying that this will happen in the future, but the 25% might be underestimated. Like the frequency of occurrence might be a little underestimated for past and future, or I don't know, like statistics are weird. Like it's kind of like flipping a coin a bunch of times in a row. You can get a whole bunch of heads in a row, and it's still a 50-50. And so like could have just been I don't know.
Well, what about the spread in the blue and the green dots between historical and current? And then and extremes, yes, it could be the orange dots, but it also could be extremes in terms of how high reach and how high the green dots reach, right? Because it's worse and worse, right, as you go up on the y-axis.
Yeah, I'd say that the green dots probably like show kind of the shift towards worse more clearly than the blue dots. I guess maybe just because it maxes out at 0 on the bottom end. But I think it's a significant shift.
And what do the farmers do when there's less than full allocation? What's their response to that?
Groundwater pumping. Though if you're having to pump groundwater more often and in larger amounts, have the water level of the groundwater is going to go down. Those who can afford it dig deeper wells. Other people can't. And then there's also like river and groundwater interaction where water's flowing between them. And
So this year, yeah, well, also this year. So this year, the allocation is about somewhere between 10 and 15%.
Okay.
The full allocation for Elephant Butte Irrigation District. And so the response, yes, is to use more groundwater, but that's typically for the,
also like if you plant less acres.
yeah. But some of the crops, like the pecans, are perennial. And so they don't have any choice. They have to continue to irrigate, but that comes from groundwater, which is resulting in groundwater depletion. So one more comment, and this is just a comment, and it's a very nice one. So it says, great work on this. This is from Ben Holland. Great work on this, Robyn. Thank you for all the great work. Take care all. So what's your response to that, Robyn?
Thanks, Ben. I think he left.
Yes.
Thanks, Teresa, for inviting Ben. I didn't think to invite him.
So any more questions or comments? I also just want to quickly acknowledge Luis Garnica, who's on the call here, who is at the University of Texas, El Paso here, who has been extremely helpful in navigating the coding aspects of Robyn's work, and not just the coding aspects, but also has been very insightful in terms of interpreting the results and so on. So just want to acknowledge Luis. And Luis has a comment, and great work, Robyn.
Thanks.
Okay, well, thanks very much to the audience for listening to Robyn's presentation and all the really great and insightful questions and comments. So more comments, Robyn, about clear presentation, great slides, very nice job, Robyn. Incredibly interesting and slightly scary.
Sure.
So I think at this time then we'll excuse the audience except for the committee members. And again, thanks very much for your participation. And let's have another round of applause for Robyn. Either